Hey guys, so we need to finish up our discussion of chi-square now. The last time in the last video we talked about the chi-square goodness of fit test that uses just a single nominal variable. What happens when we have two variables being manipulated at the same time and we're still breaking assumptions? Well, in that case, as long as the situation fits, we can run a chi-square test for independence. That's what we want to look at now. So we're going to do so using the 6 steps because for the most part we can do a lot of the 6 steps with this, and that'll help keep that sort of schema that we've been using for all of our hypothesis tests. So apologies if you're sick and tired of the 6 steps, but this literally will be the last time I have to show it to you. Okay, so the chi-square test for independence. Excuse me, there's a few new things here. So we have some of the same terminology, right? We still have contingency tables that'll tell us the observed data as well as the expected data. We have the same symbols. The chi-square is still like a little x, a chi, right, with a square over it. We still have E for expected and O for observed, so all that's the same. We just now have two variables instead of one, right? A nominal independent variable and potentially a dependent variable that is not interval or ratio, right? And so, like a typical experiment where we have an IV and a DV, but the DV has violated some of those assumptions. So we're going to have a few new formulas corresponding to a few new things we have to calculate here. In order to find the expected values for each cell, we're going to use a formula that takes the total for that column, divides by n, the total number of observations, and then multiplies that proportion by the total for the row. Okay, I'll show you how to do this. It's pretty easy. And if you do that for each of your cells, you get the exact expected value that you should have in each one of those cells. We're now going to have three different types of degrees of freedom for the chi-square instead of just the one chi-square degrees of freedom. We now have a degrees of freedom for rows, for whatever variable we represent as rows. We're also going to have a degrees of freedom for columns for whatever variable we represent as those columns. And then we're going to have an overall chi-square degrees of freedom, which is just the product of those two other degrees of freedoms. Okay, there are a few different ways of calculating expected value, but the reason why we're using this formula that might look a little bit cumbersome is because it's reliable. The other methods don't always give you what you should be using for an expected value. Well, excuse me, whereas this one will always do so because it doesn't rely on some of the assumptions that the other methods have. Okay, so have you ever heard of the healing power of laughter? Heard that when somebody's in a positive mood through recovery, they're more likely to have a strong prognosis, right, and a stronger recovery than individuals who are depressed or sad throughout any kind of medical recovery. Well, that's actually the basis, in fact, of a lot of the research as well as practice of a doctor named Patch Adams. So there was a great movie a number of years ago where Robin Williams played this character, Patch Adams, but the character is actually based on a real individual, this guy named Patch Adams. We actually had him speak on campus a number of years ago in the behavioral sciences department. This is actually a picture of him, not from that meeting engagement. In fact, if you'll believe it, he was dressed even more extravagantly on that particular occasion. And I actually passed him in the hallway, and I thought it was funny because he turned to me and said he liked my outfit. And I thought, wow, I must be wearing something really extravagant if Patch Adams likes it. But anyway, Patch would go into hospitals and he would essentially clown around and tell jokes. He would still do all the medical stuff that a doctor should do, but he would, in addition to that, try and bring some laughter, some levity, some happiness to the situation. He believed, and there's some sort of loose evidence around this, that that positive attitude and that positive mood, including laughter, can help the healing process. So, that being said, there is a researcher, Ryan, in 2006, wanted to know to what extent might comedy and uplifting feelings affect other behaviors. So, one of the things that we struggle with as a society is fertilization rates, right? There are many people who try to get pregnant who can't get pregnant. And so we oftentimes have to sort of fall back on in vitro fertilization processes. But even those aren't guaranteed. Might there be a way of increasing the success rate of in vitro fertilization? Ryan hypothesized that potentially being in a happy or laughing mood might increase the probability of your in vitro fertilization being successful, having the early level fertilization part that starts the pregnancy. And so he grabbed 186 women that volunteered, right? Divided them in half and randomly assigned them to receive either 15 minutes of clown entertainment, half before 15 minutes of clown entertainment. So they would receive, in vitro fertilization, and then they would receive 15 minutes of laughter. They would be entertained by a clown. The other group would receive the in vitro fertilization, and they would not be entertained by a clown. Note that he did not assign these people to receive in vitro fertilization. These were folks who were already signed up to do that. He simply asked if they would participate in this research study, and then half of them got exposed to a clown after the in vitro fertilization process. Okay, so does 15 minutes of clown entertainment affect fertilization rates? What data do we see at the end of this study? Well, we've got our rows divided by clown and not clown, and our columns then for which women got pregnant versus which women did not get pregnant. What we find then is that when entertained by a clown, 33 women became pregnant and 60 did not become pregnant. When not entertained by a clown, 18 became pregnant and 75 remained not pregnant. So we've got an independent variable, right? We manipulated whether or not they were exposed to clown or not clown. We have a dependent variable where we measured whether they were pregnant or not, but pregnant or not is not a numeric variable. It's a yes, no, it's a nominal dichotomous variable, and that's why we have to run a chi-square. Our data simply represent frequencies that correspond to pregnant or not pregnant, right? We don't actually have any scalar or interval ratio dependent variable. Okay, so our 6 steps. First step is to identify our populations. One population would be women who receive in vitro fertilization without seeing a clown, without being in that uplifting positive mood afterwards. Compare them to a population of women who receive in vitro fertilization, but do then see a clown for 15 minutes of uplifting entertainment. Our distribution, because we have a single nominal independent variable, and a non-scalar, right, a categorical dependent variable. This means we have to run the chi-square test because there's 2 variables. It's the chi-square test for independence, not the chi-square test for goodness or fit. What are our assumptions then? None. That's the beauty of the chi-square. We already broke all the damn assumptions. That's why we're running the chi-square test. That's an easy step. What are our hypotheses then? One of our hypotheses has to be that there's no association between clown exposure and pregnancy rates, right? That it's not going to work. That's going to be our null hypothesis, right? Remember, this is a test for independence, so we're asking whether these 2 variables of exposure to clown and pregnancy rate are independent from one another, or if there's some dependence. The dependence that we predict with our research hypothesis is that there is an association between clown exposure and pregnancy rates. Specifically, we probably would predict then that there's an effect in such that those who are exposed to in vitro fertilization are more likely to become pregnant if exposed then to a clown as well. Okay, so how do we get our degrees of freedom for this particular example? Well, I put the data up there so we can still sort of follow the rows and columns idea for now. We've got 2 rows, right? We've got clown and no clown for our independent variable, which means k of row is 2. 2 minus 1 gives us a degrees of freedom rows of 1. We see the same thing with the columns because our variable there is pregnant and not pregnant, those 2 levels. So k is 2 there, so 2 minus 1, and our degrees of freedom column is also then a 1. Lastly, our chi-square degrees of freedom is taken as the product of the other 2 degrees of freedom. So we take the 1, we multiply it by the other 1, and we get a whopping 1. All right, so that's easy because that means that our cutoff value is the same as in the last video's example where we had the same degrees of freedom. It means that with a 0.05 value and a degrees of freedom of 1, our cutoff value is a 3.841. So now we just have to calculate our expected values, and then we have to work through our observed and expected. Now, this is a little bit different from before because we have to calculate expected differently because we have these 2 different variables that we're seeing independence for. So remember, the formula doesn't change. We're still going to look at the sum of the observed minus the expected squared over the expected. So in order to do that, we come up with expected values. And these, in fact, are our expected values for these data. So if 51 women became pregnant and 135 women were not pregnant, you would expect then that roughly half of each of those groups would end up in the clown and no clown group. Or said differently, out of the individuals that received a clown or no clown, the same proportion of folks that became pregnant should be there in both cases. But how the hell did we get those numbers? Well, that's what I have to show you with that formula with expectations, right? Where we take the total of the column, divide by n, and then we multiply it times the total of the row. So let's get some of this information out of here first. What's n? We know that you recruited 186 women, and if you were to add the cells in the middle there, it would come up to 186. You can also do that via the columns or the rows, right? The totals at the end. And so what we need to do then is take that, we need the total column, and we need the total row. So let's start with our top left cell, the clown and pregnant. When it was observed, it was 33. In order to figure out the expected, we have to take the total of that column. So the 33 plus the 18 for all the pregnancies is 51. So you'd put 51 over 186. You then have to multiply that times the total for that row. So if you look all the way to the right, you can see the total for that row is 93. So then in the formula between the two tables, you can see the top left one of those calculates that, and we end up with 25.482. You end up with the exact same information for the cell right below that, where it's pregnant and no clown, because you use the same information on total in the column, the total N, and the total row. We move to the other side of the table now for when women were not pregnant. We take the total of that column, which is 135. We divide that by 186, and we multiply it then by the total for the row, which is 93, and we get to 67.518. So that's a lot of talking really fast, but play it through a couple of times. It's a really easy process to do, okay? And the formula is super easy to follow. Okay, so now let's load it up into our table here and calculate through. Let's put all our categories, our 4 different cells over in the far left column where we had clown and pregnancy, clown and not pregnancy, no clown and pregnancy, and no clown and not pregnancy. Put our observed data in there, just like we've had since the beginning of this problem, 30, 60, 18, and 75. Transport over your expected values that you just calculated on the previous slide, 25, 67, 25, and 67. We now have basically everything we need. We just need to do observed minus expected, right? That next row, next column. We then need to square that value. And then lastly, we need to take that value, divide by the expected values that are all the way over there in that middle column. So we subtract it, we square it, we divide by expected, and then we sum all of those up, and we get a chi-square of 6.081. Remember, our critical value was a 3.841. This means that our chi-square is further into the tail. It means it's unlikely to be due to chance alone, which means that this relationship we've observed is a real relationship, and that those two variables are not independent. In fact, you could say that there is an association between exposure to clowns or humor and pregnancy rates in women who received in vitro fertilization. Women who received clown exposure were more likely to become pregnant than women who did not receive that clown exposure. So again, remember the chi-square is written in APA style a little bit differently. You include the chi-square degrees of freedom, the n, and then the rest of it seems to be very similar to what we've done in the past. One more thing though, in this particular form of chi-square, we can actually display our data really easily, and we can calculate measures of effect size. So let me show you how to do that real quick. How would you display these data? Well, actually easy. You have 4 numbers in the center of the table that are relevant, and you can do these as proportions, percentages, rather than actual frequencies if you want to. So 75 out of 186 is a little less than 50% of the sample, right? And so if I graph it in this way proportionately, you could see that when there was a clown, the difference between not pregnant and pregnant is a little bit smaller because the number of individuals who end up not pregnant goes down, and the number of individuals who end up pregnant goes up. That percentage is a little bit more exacerbated over on the other side with the no clown, fewer percentages or a fewer proportion becoming pregnant in that particular exposure group. So it's really easy to display these data. And again, we don't want to forget that the whole point of statistics is not just to test our hypotheses, but to be able to display and to convey those patterns back out to other people. Lastly, with respect to this example, a measure of effect size, right? We can use Kramer's V in this case. So after we've made our conclusion that there's an association between exposure to clowns and pregnancy rates in women who received in vitro fertilization, can we say how large that effect is? Is it massive? So massive that if we really, truly want to increase the rates of in vitro fertilization, then we should invest in making sure that women get some sort of entertainment, some humorous entertainment after the procedure? Or is it a relatively small effect and perhaps not worthy of that investment? Well, Kramer's V could tell us that, and it's a pretty simple formula where you simply take the chi-squared and then divide by n times the degrees of freedom for the row column. That's your degrees of freedom chi-squared, and then just take the square root of that. So for our example then, it'd be 6.08, our chi-squared, divided by the 186 total times the degrees of freedom of 1. Take the square of that, we end up with a 0.182. Kramer also then gives us conventions for cutoffs there. So when our degrees of freedom is 1, so that's the first column, we see that a small effect size is above 0.1, so between 0.1 and 0.3, which means that our effect here is a medium effect size. So again, The chi-square test is a really useful non-parametric test for when we encounter data that break those assumptions, and not just because we have the singular variable, but sometimes because we have two variables, but one of our variables is just not interval or ratio. So again, try and remember this when you move beyond the class and you do have to collect data for whatever it happens to be, an independent study, a job you're working for, that even if you violated some of the assumptions of a traditional hypothesis test, you can still use these non-parametric tests.